Good morning, everyone. So you may have noticed I sent out an email announcement about mesh workshops. There's another one coming up for preparation for quiz 4. So the announcement with the links is there on views. You may be familiar already with the mesh homepage by now, hopefully. If you go to the events, workshops, and programs section, you'll see there's a whole bunch of events for a whole bunch of different units. Right down the bottom is where biometry is. And you can see for Campbelltown campus, they're holding a preparation workshop after the lecture next week. Okay, so please register for that if you're interested. Everyone always tells me that the mesh workshops help them a lot when they go to them, especially if you have been struggling with the quizzes so far, or you didn't do as well in the computer skills test as you thought you would. Then make sure you get as much help as you can with the last remaining quizzes, okay? And the other thing I will say about that as well is don't sort of put your prac activities to the wayside now just because you've done the computer skills test and feel like they don't matter anymore. I made a little mention of that at the end of this announcement. I didn't email this one, I just posted this one. To make sure you don't forget about your prac exercises, aside from the 2 quizzes that you still have remaining, there will also potentially be R-Commander output in your final exam paper, and you're expected to be able to interpret it and analyze it and calculate things based on that output. So yeah, don't just forget about your prac exercises now, even though the computer skills test is done. I have posted a sample final exam there in the assessments tab. I won't post the solutions yet, if at all. Probably in week 14, I'll go through the sample paper with everyone, but it's there now so that you can see it. I put it up straight away because I just did want to point out that you may get stuff like this, in the final exam. So you'll be given R-Commander output. Obviously, it's a written exam, 2-hour written exam. You're not expected to use a computer or anything like that. You can't. But you will still have to know how to deal with R-Commander to make it through the final exam. Okay, there's maybe a few questions based on that kind of stuff. As a point of interest, I also put up the average marks for the computer skills test. So Campbelltown was at the top of the pile, 18.1. The overall average was 17.4, but I did an analysis of variance test on the raw data and found that that wasn't a significant difference between the campuses. The p-value was about 30%, 0.297, which means that there's about a 30% chance that you would have gotten averages like that, just even if there were no difference between the campuses. If we ran the test again next year, which we will, obviously, and analyze the data, the whole thing could be reversed. Okay, so the point is that it looks like there's a difference, but it's not a statistically significant difference between the campuses. The only reason I mention that is just I thought it was a good exercise, just another good way to wrap your head around analysis of variance. You've got a difference of means between more than 2 things, 3 campuses. Which also would have featured in your computer skills test. So difference of means, yeah, they're different according to the sample statistics we've got. Is it a significant difference though, or could it have happened just by chance? Okay, turns out about a 30% chance you could get that even if there's no difference between the campuses. The data was also really normally distributed. I was quite surprised. I didn't expect something so neat to come out of the data, which is kind of pleasing. I mean, you always hear that normal distributions do tend to occur in real life and in nature. You've got an average and things are sort of on a bell curve either side of that. And I was really surprised to see how close the sample data from the computer skills test was to that. You can see there's only a single point, or maybe 2 points, I think, down the bottom there, that were outside of the confidence envelope. So yeah, I just thought that was interesting. And again, I thought it was a good exercise just to give you something to sink your teeth into and think about. I think a lot of people get lost with all the abstraction and the stats and stuff like that and don't think about what it is you're actually doing. So there you go. There's an actual real-life example. Analysis of variance on some real data, and that's what we got. Okay. Any questions about the mesh workshop or anything? So it'll be next week after the lecture from 11 to 12. Okay. So this week is continuing on from what we discussed last week, which was correlation and simple linear regression. We're going to be a little bit more, I guess, go into a little bit more detail this week. We'll do a quick recap of everything that we did last week. So we had a set of data last week. It was 9 pairs of numbers. Sorry, that mic is still a little bit loud. we had 9 pairs of numbers, and we had one set of numbers was the length of the bone in your hand, and the other was your height. So we wanted to say, can we predict someone's height based solely on that information about the length of this bone in their hand? And that was a linear regression problem. We found that the correlation between those two variables was quite high. It was about 0.856. So that told us that there was a pretty strong correlation between those two variables, okay, in a linear sense. Okay, one was increasing with the other at a constant rate. That was the key, at a constant rate. So we wanted to use that concept, right? If one increases according to when the other one increases at a constant rate, can we use that information to then predict anyone's height based on the length of their metacarpus? So we did that. We got an equation of a line that best fitted the data. There's that red line through our 9 points. And we used that to make some predictions. You know, we said, oh, if someone's got, you know, a length of their metacarpus is 43, using the equation of our line, we can therefore predict that they'd be about 167 centimeters tall or something like that. Okay? Pretty basic concept, but the maths behind it was a bit difficult. But again, the maths behind it is not something that you're expected to ever reproduce or to work with that much. RCommand will do all of the heavy lifting for you. But there may be a few occasions where you're asked to calculate something like a test statistic or you know, a simple calculation for the slope given some sums of squares or something like that. So just a reminder about the terms that we used. We've been using predictor and response variable for most of the discussion, but also there are two equivalent names. Maybe I'll color code them. Response and dependent for the y-axis, or predictor and independent for the x-axis, okay? The idea is that whichever variable you think is going to predict or explain your other one, you call the predictor or the independent. The other one, therefore, responds to or is dependent upon that other variable. So x and y, response and dependent. So we got an equation of a line, y equals a plus bx. Overall, the linear model then is described by the equation of that line plus some kind of error, which we denote with the Greek letter epsilon. And we say we've got the equation of our line. Obviously, all the data points don't fit exactly on it, so the model is the line plus or minus a certain amount for each point. So A was the y-intercepts, the point where that line crosses the y-axis. B is the slope, that's its gradient, how steep the line is. And is it a positive slope or is it a negative slope? And then we needed to estimate those two values, A and B. We've got two variables. We think that they are related. There should be some linear relationship between them overall in the entire population. We can't look at the entire population, so we can't get an exact model, an exact linear model. We need to estimate those two values, A and B. And we saw that last week the way to do that for the slope was we got an idea that was similar to calculating rise over run like you would in high school for an equation of a line. But because we had a scatter plot, our rise was the standard deviation in the y's, and our run was the standard deviation in the x's. And then we had to modify that by how closely correlated the two variables were. And at the end, it came out to be that. Okay, it came out to be that expression, SXY over SXX. It was a bunch of sums of squares divided by each other. And then A hat, you need B hat to work it out. Once you've got B hat, A hat depends on the mean of both of your variables and the slope estimate. So that's a recap of everything we did last week. There's nothing new there. That were the numbers we got. And these were the assumptions that we talked about. And the last 2, 3, and 4 are the assumptions that we're going to spend more time on today. So the first two assumptions that we make when we do simple linear regression are that there should be a real linear relationship between the variables. I mean, it almost goes without saying, but obviously, if you're doing simple linear regression, you're assuming that there is an actual linear relationship between those two variables. And secondly, the observations should be independent. The second one there is more to do with your experimental setup rather than the maths and the stats. So it's really 3 and 4 that are the ones that are going to interest us, and we'll talk more about them at the end of the lecture as to how you can check your assumptions. We haven't really done that much in everything we've done so far. We've had assumptions. Every time we've calculated a test statistic, whether it was for analysis of variance or single samples or whatever, we listed a few assumptions that went with it, but we never discussed what do you do if it doesn't satisfy those assumptions, or how do you check if it satisfies those assumptions. With simple linear regression, we'll go into a little bit more detail and say, how do you actually check that these two things are true? Okay. So first up, we'll talk about something called the residuals. So the residuals is the difference between what you observed in your sample data for the y variable and what was predicted by your linear model. So here's your linear model, y equals a plus b times x. The residual is the difference between that value of y that was predicted by the model and the actual value that you had. So if we go back to our picture, we've got residuals for every point in the scatter plot. Here's 1 point. This is the difference between the observed value of y, I'll call that y1, and the predicted value of y, I'll call that y1 hat. So that gap there, that vertical gap, is the residual. I'd call that R1, first residual, R2, second residual, R3, and so on for all of them. Okay? So that's why they're called residuals. It's kind of like what's left over. You've got the equation of your line. It makes a certain prediction, but it doesn't quite get there. What was left over after that? What's the difference between what you saw and what you expected? That's the residual. That's the leftover bit. Okay? So that's all it is. Very simple. Just the difference between two numbers. What did you see? What did you expect? Happy with that? We're going to look at the squared residuals. We're going to use them fairly extensively. So the squared residuals is we're going to add up all of these squared residuals and then divide by the number of independent values in that expression. So I've put here on the right-hand side, if you remember, the residuals, as we just described, is the difference between what we saw and what we expected to see from the linear model, y hat. And y hat is calculated according to that expression, a plus b times x. In that expression for y hat, we calculated two estimates, one for a hat, one for b hat. And if you remember in the past, anytime I've made a discussion about degrees of freedom, I've said that every time you calculate a sample statistic, you use up a degree of freedom. So when I calculated a hat, I've used up 1. When I calculate b hat, I've now used up 2. And that's why we divide by n minus 2 when we take the average squared residuals. Okay? So that's what this s squared is here. It's called s squared because we've used s in the past for standard deviation and s squared for variance. And this is the same thing. That's why we use the same letter, s squared. It's just another way of talking about variance, but in the context of simple linear regression. You take all your squared deviations, right? That's what variance is. How far am I from the mean? But this time, instead of saying how far am I from the mean, I'm saying how far am I from the linear model, from the predicted value. Take that difference, square it, add them all up for every point that you've got, and then work out the average, which you divide by the number of independent things, which in this case is n minus 2, because we estimated 2 statistics to get there. Okay? So it's an estimate of the variance of the response variables around the line. And this is where we're starting to get to the pointy end of the semester. The ideas are getting more sophisticated. But does anyone remember from last week, the variance of all the y values around the line, what should it be as you change your x-axis value, as you move left or right, whatever? How does that affect the variance around the line if we're doing simple linear regression? Or how should it affect it? Does anyone remember? It was one of those assumptions that we looked at before. It shouldn't affect it. The variance around the line should be a constant number. So I've got my sample data. Sure, this is just sample points, but in the real population, for every value of the predictor variable, I would get however many values for the response variable. Two things that we said about that response variable for every point on the line is that it should be normally distributed around the line. And what was the second thing about those points? Should be normally distributed, and they should all have the same variance. Okay, it should be the same spread. And I don't know why OneNote has frozen on me. Yeah, so wherever you go on the line, I should be, if I were able to take more and more observations for every individual value along the x-axis, I should see that they're mostly densely clustered around the line when it comes to looking at the points for the response value. Very densely clustered around the line. They start to tail off as they get further out because it's normally distributed. And the spread of those points should be the same, no matter where I move along the line. Okay, it should have constant variance. Why have you died on me? All right, give me 1 second. Let's try this. Draw. Nope. Okay, I will just have to restart. Give me a second. This doesn't happen often, but enough to be annoying. Oh, you are kidding me. So it just crashed on me. I've been pretty happy with my Service Pro up until now. Hey? Yeah. Anyone got any questions while we're waiting?
Can you sort of explain what you were doing before with the dots?
I was definitely meaning, I'll definitely go into more detail on that. As it froze, I was halfway through the explanation. I meant to illustrate more of it. Yeah, I really need to get to draw it to really describe what I was doing with those dots. All right, let's try again. Maybe I've tried to make it do too much in one go. I plugged the display port in, I started trying to draw, and I think I got confused with so many things going on. Okay. Okay. All right. We should be good. So these dots they basically represent, if I took an individual, let's say me, measured the length of the metacarpus bone in my hand, it was, let's say, 43 millimeters. And then I find someone else who has the same length, 43 millimeters, find someone else. I get a bunch of observations, all of them over 43 millimeters, right? For each person, I measure their height as well. So that's why I have a bunch of different points. They all have the same length of bone in their hand, but they're not all going to be exactly the same height necessarily. However, they should be pretty close to the same height, pretty closely clustered. If I could take 100 individuals with the same length of bone in their hand and measure all of them, most of them should come out to be somewhere around that, looks like about 165 centimeter kind of mark. But then obviously you get a few points outside of that, okay? And there's a certain spread to those numbers, right? You could look at just the Y values for every single one of those points, and you've got one set of numbers. What's its variance? What's its standard deviation? I could ask that. And I could work that out. It's just you work it out the same way you work out variance or standard deviation for any other set of numbers. The point is, if I did that again for any other value, let's say I go to 44 millimeters, so I find a whole bunch of people who all have 44 millimeter metacarpus bones and measure their height. And again, most of their heights should probably be pretty close to the value given by the line. Okay. They're going to be pretty closely clustered around the center, but then you will get numbers further away from that, but not very often. So it's normally distributed, but the point is that the variance is the same. No matter where you go along the line, they should all have roughly the same spread around the line for every single point. So my scatter plot, in the end, if I were to take a lot of numbers, I should see something, pretty much where all the points lie inside a corridor. A couple of parallel lines either side of the line of best fit, because the variance is the same. If I see something like this, I've got points really close to the line down the bottom, but then they get spread further and further and further apart as I go along. Well, that doesn't look like I've got something linear happening at all. Okay, it's sort of spreading out. The variance depends on the value along the x-axis. It gets bigger as x gets bigger. Or it could go the other way around. It could get smaller as x gets bigger. Okay? The point is, though, it's not constant. It's changing as x changes. That's not what we want to see in linear regression. Okay? It should be the case. So here's one where it gets smaller as x gets bigger. Okay? So it's fanning out this way now. That should not be the case. That doesn't represent something linear. Something else is going on there. It looks a bit logarithmic or something like that. Okay, so I want the variance around the line to be the same for every single value along the x-axis. Does that make sense? Yeah? So our best estimate for that variance is going to be the squared residuals. Okay, I take all of those residual values, because obviously in this case, I've only even got 1 point for every x-axis variable. I don't even have more than 1 for every point. So I have a residual at this point, at this point, at this point. I take each of those numbers and square them and add them all up. And then I say, what was the average? I divide by n minus 2. And it gives me a rough sense of the variance of all the numbers around the line. That's my best estimate. That's as good as I can do based on the sample data. Okay? So that's why we're going to use the squared residuals. Still just talking about variance, really. So this guy here on its own, if I ignore dividing by n minus 2, I just call that on its own the residual sum of squares. And we are going to abbreviate that later as RSS, residual sum of squares. So that's what you get when you don't divide it by n minus 2. So we haven't said much about that yet, but we will use that later on. So we did a hypothesis test last week on the correlation coefficient. And we wanted to say, sure, given our sample correlation, it looks like there is a relationship between these two variables. They seem to be pretty closely linearly correlated. The correlation was about 0.85, so pretty strong linear correlation. But we said, okay, it looks strong based on the sample data, but is it actually strong? Is that a significant correlation? Because the sample only has 9 pairs of observations. It doesn't seem like a huge sample size, does it? And when you have very small sample sizes, they tend to be prone to very large fluctuations in the variables. It's possible to get something that looks significant that's actually just a fluke, right? Like flipping a coin 5 times in a row and getting 5 heads. I mean, that seems unlikely. It could be there's something wrong with the coin. It's unbalanced. It seems unlikely. But it's also possible it could have just been a fluke. Sometimes you flip a coin 5 times in a row and get 5 heads, right? It doesn't mean there's something wrong with the coin. It just means sometimes that happens. So that's the whole point of hypothesis testing. Everything we've done this semester is to say, okay, it could have happened, but how likely is that? And we said that the likelihood of getting a correlation that big, 0.85, was very small if there were actually no correlation happening at all. I think the p-value we got was less than 1%. So we're going to do the same idea, but for the slope. We're going to ask the question, is the slope of the line that best fits the data equal to 0? Okay. The reason we ask that question is because really we're asking the same question as we were when we did the correlation test. Correlation said there's no relationship between the variables if rho is equal to 0. It actually means the same thing if the slope is equal to 0. Because if the slope is 0, you've just got a line that goes flat, horizontal, straight through the plot, which means that no matter what your x value is, you can pick any x value at all, the y value is always the same. Y doesn't depend on x. It has no effect on y when you change x. Y doesn't respond to x as the response variable. So asking if the slope is 0, we're going to see is actually equivalent to asking if the correlation is equal to 0 or not. So we're going to do a hypothesis test. You can also do a hypothesis test on whether the intercept is equal to 0 or a specific value, but it's just not an important question, really. We rarely care where it crosses the y-axis, because usually where it crosses the y-axis wouldn't even make any sense physically. Like when we talked about stature and the length of your metacarpus, there was a predicted value for someone who has a metacarpus of length 0, right? The predicted height was about 95 centimeters. But so what? No one has a metacarpus of length 0. Even a newborn doesn't have a metacarpus of length 0. So it's not a sensible thing. So we're usually not that interested in the y-intercept, but if you wanted to, you could do a hypothesis test on it, but we're not going to worry about it. We're not going to talk about the test statistic for that because it's not an important thing. For the slope, though, we want to get a test statistic. We want to say, here's our estimate for the slope. Is it significantly different from 0 in terms of some kind of standard error? Okay. And this is the same format that we've used a fair few times until we got to analysis of variance, basically. What did I get minus what I expected to get over the standard error? So this goes way back to the central limit theorem that we discussed many, many weeks ago. We had a population, some kind of population of values. From that population, we take a sample, and from that sample, we calculate a sample statistic. In our case, we're interested in the slope, the line that best fits a population of two sets of numbers. We calculate an estimate for the slope. That estimate, oops, that's a terrible picture. That estimate should be pretty close to the real value in the population, right? There is some value. The real value of the slope of the line that best fits the entire population of these two sets of numbers. Every time I calculate a sample, I expect to get pretty close to that, pretty much in the ballpark, right? Because the central limit theorem tells us it should be something that looks like a normal distribution or a t-distribution. Should be peaking around the true value. Most of the time, I should get something close to the true value. Like the mean for the computer skills test was 17.4. If I do the test again next year with a whole new set of students, I'd expect the mean to come out to be somewhere pretty close to that. Okay, I don't expect a huge variation. If I don't change the test at all, and I don't change teaching style at all, I should get something pretty close to that. Sometimes you don't, right? Sometimes just by a random fluke, you could get a year of completely terrible students and get an average of 10. It happens. It doesn't necessarily mean anything has changed in the population. Sometimes it just happens, right? So that's the idea behind the central limit theorem. I should be getting a sample statistic pretty close to the real value. Sometimes it will be very far away, but it doesn't happen that often. That's what the p-value is. It tells you how likely is that to happen if the population really does have a value equal to that one. So this is going to be our test statistic for the slope. It's got this same basic format. We say, what was our sample statistic minus what did we expect? Now, we're doing a hypothesis test for it being different than 0. So that's what my null hypothesis says. It should be equal to 0. That's what I'm expecting to see. How big is the difference between my value and what I expected to get in terms of the standard error? So the standard error is the standard deviation of this guy here, right? A measure of the spread of this guy, SE. Standard error is just standard deviation, but specifically, it's the standard deviation of the distribution of sample statistics, of whatever sample statistic you've got. In the past, we dealt with the sample mean, right? It had a distribution that looked like that, and it had a standard error that we calculated as being the population variance divided by the sample size. This time, we've got a new sample statistic. It looks very different to a sample mean. It's now a slope of a line based on a scatter plot, right? But the idea is the same. What is the approximate spread of this distribution? That's the standard error. So we say, how far away am I from 0? That's what I expect to get. Here's what I actually got, down here somewhere, let's say. How far away is that in terms of multiples of the standard error. And that will then allow me to calculate a p-value, the probability of getting something bigger than that. So that's the idea. We won't go into why the standard error comes out to be this guy. It comes out to be that sum of residuals, those squared residuals that we added all up. We said that was s squared, going back up here. There you go. So s is just the square root of that. Okay, it's a measure of standard deviation of all of the y values around the line. So that's s. And sxx, if you don't remember from last week, was almost the variance, but again, we just didn't divide by n-1 when we did the calculation. So we gave it that special name sxx, the sum of the squared deviations of the x's. You'd have another one for the squared deviations for the y's, would just be yi minus y bar. So that's it, that's our test statistic. That'll allow us to quantify how different our sample slope is from what we expected. Specifically, it will follow a t-distribution with n-2 degrees of freedom. So that picture that I was drawing was not a perfect normal. This guy here is a t-distribution with n-2 degrees of freedom. Okay, where is our sample stat in that distribution? That'll allow us to calculate the p-value. So none of that is new. I just thought it was a good time to recap. It's been a while since we talked explicitly about standard error in terms of, the central limit theorem. Any questions so far? So we're just doing a hypothesis test. Is the slope estimate different from what we expected? You can have 3 alternative hypotheses again. So this is going back to when we did single sample testing. You've got a 2-sided version for not equals, and then you've got one for greater than or less than. They're both one-sided. So let's see what we actually get from our sample data. So this is all the stuff we talked about last week. Super complicated looking. But again, you'd never be expected to calculate the numbers given by hand. You would be expected to read them off from RCommand output. So we'll go through that in the pracs, obviously, and when we do the sample final, if there's one there. But you do need to then know, given those numbers, how do you calculate the test statistic? So just to remind you what all these numbers are, I mean, x bar and y bar, that's basic. You've done that. Sample means for each value, each variable. sxx and syy, they're the sums of squares of the x's and the y's. So I've drawn everything over on the right-hand side there, just to remind you of what those formulae represent. Sxy is the product of the differences of each variable value from its mean. And RSS, that's the one we said was the sum, residual sums of squares. So you plug all that into your formula. S squared is the residual sum of squares divided by n-2. That comes out to be about 18. So that's our measure for the variation in stature, in height, around the line. It's about 18 centimeters, 1 standard deviation. I expect all the values that I get, or most of the values that I get, for any given value of the length of your metacarpus to be within about plus or minus 18 centimeters either side of that line. So that's a measure of your variance. The standard deviation is then the square root of that number, 4.255. Okay, it appears down there as s rather than s squared. You get sxx, 120.2, square root it. The moral of the story is that right at the end we get our test statistic. It's a single number, 4.38, that tells us that our sample estimate for the slope is about 4.4 standard deviations from what we expected to get, according to the null hypothesis. We were expecting to get 0 if the null hypothesis is true. Do you think the p-value for that test statistic would be big or small? You don't need a computer to basically have an intuition for whether or not the p-value should be big or small for that. Big? Big Y. Small. Yeah, it's small. It's small. So again, think about what we've got. We've got a t-distribution, right? T-distribution looks something like that. It's centered on 0. We got a test statistic of about 4.38, all the way up there, right? 4.3 standard deviations, yeah. So because it is a 2-sided test, a null hypothesis said the slope was equal to 0. The alternative said that it was not. It's a 2-sided test, so I need to take that number, look at whichever area is smaller. It could be to the right of it if it's positive, or to the left of it if it's negative, and then double it. Or equivalently, you say, where's 4.38? Look at the area to the left of that. So the total area, those two red shaded areas, that's your p-value. You're quite a way off the center, okay? So that area should be very small. Remember, if you go even 2 standard deviations either side of the mean for a normal distribution, you've got about 95% of all values. So you've got 5% outside, which is already getting close to our significance level, right? If you go 4 standard deviations, you are way outside that range. The p-value is probably going to be less than 1%. In fact, the p-value is less than 1%. It's 0.0032 for that test statistic. So there's evidence that the slope is not 0, right? It seems like there is a relationship between these two variables. Specifically, in this case, it's a positive slope, but definitely it doesn't look like it's a fluke. There actually is a relationship between the metacarpus and your stature, okay, according to our test that we just did. That's the p-value we got from a t-distribution with n-2, 7 degrees of freedom for our example. Does that look familiar? Anyone who's got, I mean, really, you probably only have to you'd need a photographic memory to remember why that's familiar. That was from last week. When we did the test, as I said, for correlation being different from 0, that's the exact same test statistic and the exact same p-value. Exactly the same. That's not a fluke. That will always be the case for simple linear regression when you have only a single predictor or explanatory variable. Testing for whether or not the slope is different from 0 is completely equivalent to testing for whether or not the correlation is different from 0. They're really asking the same thing in a different way, right? As we said, if the slope is equal to 0, you have a line that best fits your data that's completely flat. No matter what your x value is along the x-axis, y doesn't change at all. So there's no relationship between them. They're completely independent, which is exactly what the correlation coefficient would tell you as well if it were equal to 0. So they're both asking the same question, but answering it in a different way, using a little bit different maths, okay? So it's not an accident that the test statistic and the p-value came out to be the same as the test we did last week. That will always be the case for simple linear regression, okay? If the alternative hypothesis were different, and it's worth spending a bit of time on this because I still tend to find, out of all the things that we do, calculating p-values, not even calculating, but just thinking about what they should be based on the null and alternative hypothesis still tends to throw people. And if you want some practice with this was all in worksheet 5. So you were given a bunch of theory questions that said, here's your alternative hypothesis, and here's a number. Didn't tell you exactly what the specific reason for the number was. They just said, this is the number that you would get if you exceeded the test statistic or got less than the test statistic or whatever. It was then up to you to work out, is that number your p-value? Is your p-value twice that number? Is it 1 minus that number? Or is it twice 1 minus that number? Depends. Depends on what the alternative hypothesis is. So we just did that for alternative hypothesis of not being equal to 0. If I said less than 0, and there's my test statistic, now what should my p-value be as an area in the curve? Everything to the left of it, everything to the left of it. Everything less than the test statistic. If my alternative hypothesis says less than, then my p-value will be everything less than that. If my alternative hypothesis says greater than, no surprise, my p-value is going to be everything greater than that, okay? If I was looking for evidence that it was greater than, but my test statistic actually came out to be negative 4.38, well, I should get a huge p-value. But again, it's consistent. I'm looking for greater than. There's the area greater than my test statistic, okay? It's going to be very large. I should not have evidence that the slope is greater than 0 when my slope came out to be less than 0, right? That would be nonsense. That makes sense. The p-value is very large in that case. So I would recommend worksheet 5 as a good worksheet to go back. It's really quite central to the rest of the subject, understanding the test statistics and the p-values in terms of the null and alternative hypothesis. It really will help you with everything else that you do in the unit. So any questions about that? We just did a hypothesis test for whether or not the slope was different from 0. Happy? Okay. All right, so now we'll talk about those residual sums of squares a little bit more, because we're going to calculate a new number, a new way of quantifying something about our scatter plot. And this number is called r squared, or also the coefficient of determination. Those are the two names that it goes by. We'll talk about why it's called R squared in a little bit. You could probably guess, if you've been paying attention, why it's called R squared. Does anyone want to take a stab in the dark? It's related to residuals, but why? So that's the R, but why is it R squared? Don't worry, we'll get to it. So yeah, and I should also say, I just sometimes it's worth mentioning, because we deal with R so much as a programming language, some students get confused and think that there's a relationship between R and this value. This value was called R long before the programming language was around. So there's no relationship there at all. That's just a coincidence. But we're going to talk about this number, which is calculated as 1 minus the residual sums of squares over the squared deviations of the y values. And I'm going to unpack this a little bit and break it down. So I've got a picture, or I did have a picture before my computer froze. Now I have to find it again. Not that it's hard to find. Termination. I'm going to the most reliable source on the internet, Wikipedia. Anyone who tells you you can't use Wikipedia as a source is full of nonsense. It's great. I use it all the time. It's better than most textbooks. There we go. So I got this picture from Wikipedia. It's a lot better than anything I would draw. And I want to break it down for you, that expression that we just looked at. On the left, we've got a scatter plot, and on the right, we've got a scatter plot. They're the same scatter plot, but they have different lines drawn through them. On the left, the line corresponds to the average value of all of the y values, okay? So for the example we were looking at, this value might be about 171. It was people's average height. So there you go, at 171, you draw a straight line directly across it. That's your average for all the y values. Okay. What are the little squares? These little squares represent the squared residuals. You say, how far was this point from the mean, and then square it. And you can represent a number squared as a square, right? That makes sense. You can represent that as an area. So that's what we've done here. We've represented the square of that distance from the point to the mean as an area of a square. I did that last week as well when I talked about the correlation coefficient. So there's the squared residual for this point, represented as the area of a square. There's the squared residual for that point, for that point, for that point. Sorry, I should not call it the residual. That's the name for the other one. These are the deviations from the mean, squared deviations from the mean of the y's. Okay, happy with that? The one on the right is the same idea, but that's the squared residuals. So these ones are the deviation from the line that best fits the data. How far away is that from the line? How far away is that from the line? I represent all of those squared values as the area of squares. Okay. The idea is that we've got two types of variation happening. One is just the variation across all of the y values. Take them as a single set of numbers. How spread are they? What's the total variation in that population? That's represented by the red squares. The other one is the variation due to everything that is not explained by the line. I don't know if that makes sense. So I've got my linear model, and that tries to best fit the data. There will be some little bits left over though. How much variation is there around the line of best fit? That's the squared residuals. So what we want to do is take this idea and say, what is the total area here in the blue ones divided by the total area there of the red ones? And that will tell us how much variation is accounted for by the linear model. That's a little bit of a difficult concept to get your head around. How much variation is accounted for by that line? That's the idea. You can see there's a fair bit of variation in the numbers. How much of that variation is explained by the linear model that we have? Okay. So again, going back to the data we've got for stature and metacarpus length, there's variation in people's heights, right? We all know that. No one's the same, people aren't all exactly the same height. There's variation there, obviously. You could be 150 centimeters, you could be 200. Okay, there's variation there. How much of that variation do we think is related to the length of your metacarpus? That's the question. How much do we think is related to the length of your metacarpus? Obviously, there's a confounding variable, which is just your genetics. That's going to influence both of those things, but let's pretend for now it doesn't. Just the length of that bone in your hand. How much of your height can I predict based on that value, based on the length of the bone in your hand, right? How much of the variation here is due to the relationship with this bone? That's what those blue squares will tell you. How different are what you observed from what you expected according to your linear model. Okay. I think that's a good picture, but it may take some time. You may want to look at that yourself and mull it over and then go back and look at the equation, which we'll do now, and think about what it is that it's telling you. You can find that picture on the Wikipedia page for the coefficient of determination. Okay. So there's the blue ones, squared residuals. There's the red ones, squared deviations from the mean. According to our formula, our coefficient of determination is the squared residuals. So I'll put that in blue, so it's color-coded the same as it was on the picture. They were the blue squares over the reddy orangish squares, the squared deviations from the mean. Okay? That would tell me the proportion of variation that isn't explained by the line, is not explained by the line. So there's still variation in height, even after I try and predict it based on the length of your metacarpus. There's still going to be some variation. That's the blue one. How big is that as a proportion of the total variation? Okay, just the set of all heights that I could look at. They have a variation, they have a standard deviation. How big is the variation around the line compared to just the total variation of the y values? This is a very similar idea to analysis of variance. Remember we talked about the variation between the means and around the means and all that kind of stuff. Same thing's going on here. So this fraction here is a proportion. It tells you everything, proportion of variation in the y value, the response variable, variation in y that is not explained or accounted for by the line. By the line. So what happens when you subtract that from 1? You get the proportion that is accounted for by the line. R squared represents the proportion of variation that is explained by the linear model. Okay? So that proportion there gives you what isn't explained. Subtract it from 1, you get what is explained, because it's a proportion. It can only be between 0 and 1. And they're complementary ideas. Here's what's not explained, here's what is explained. They must add up to be 1, everything that there is, right? So you subtract that from 1, you get the proportion that is explained by the line. Make sense? Again, if it doesn't, that may be something you want to, as I said, mull it over yourself. Go and look at that picture and then look at the equation here. The equation is simpler than it appears, right? It looks complicated at first glance. That's why I tried to unpack it and break it down. The blue squares, the red squares, what's the difference? You know, what's the proportion of that? Subtract it from 1, okay? So this is what R squared is. It's a useful number, and you'll probably come across this number in other subjects that you do. I've heard at least, I know people doing, I mean, has anyone come across it yet in like a chemistry subject or something? Yeah. So you'll hear about it. You'll be given some Excel output or asked to work in Excel. It'll spit out an R squared number. That's what it is. It tells you how good of a linear model you have. How good a model your line is for your data. You've got a scatter plot. You get a line of best fit. How good is the line? Okay, is it doing a good job of representing the overall trend between these two variables, the relationship between these two variables? So because R squared is a proportion, it must always be between 0 and 1. Can never be anything outside that range. It's impossible. If someone tells you it is, they've done something wrong. It must always be between 0 and 1. Okay. However, we will often express it as a percentage, 70%, 30%, just like we did with the correlation coefficient last week. Okay? It's the percentage of variation explained by the line. Here's some examples, some scatter plots, and their corresponding coefficient of determination, their R squared value. So you see the top left and the bottom right both have R squared values of 100% because 100% of the variation in the Y values is explained by the line. The line does a perfect job of explaining everything that's going on. There's nothing left over after you have the linear model to describe the relationship between them. 100% of the variation is explained by the line. In the top right and the bottom left, only about 16% of the variation in the Y values is explained by the line. The line is not doing a great job of modeling this data. Okay, you can see the line, there it is. There's obviously distinct large amounts of variation of all the actual observed points around it. Okay, and about 16% of the variation in the y values is accounted for by this line. That's what it's telling you. Again, because it's an r-squared value, it's a positive value, must be between 0 and 1. They've given two graphs of the same type, basically, to indicate that the r-squared value does not depend in any way on the slope of that line. Positive or negative, the r-squared value will be the same. Okay, it can only ever be positive. Whether you've got a positive trend or a negative trend, it must be the same, okay, for equivalent things. Happy with that? Yeah. So here's why it's called r squared. It's because it's actually the square of the correlation coefficient we looked at last week. Okay, so you could calculate it based on the residual sums of squares and the squared deviations of the y's using that formula. Or if you already have the correlation coefficient, you just square that number and you'll get r squared. That's why it's called r squared. So that's only the case, though, for simple linear regression. So you can have complex regression where you try and predict a response variable based on a whole bunch of other variables. x1, x2, x3, blah, blah, blah. You could have a whole bunch of variables. I don't know how far I'm going to go down the alphabet, but yeah, there you go. You could have a whole bunch of variables, x1, x2, x3, and try and make a linear model. So it still looks like this. It's still a constant times a variable plus a constant times a variable. That is, by definition, a linear kind of relationship. So you can do that with more than one variable, but it's not something we ever bother to do. But in a case where you only have one variable, the correlation coefficient will be, when you square it, you will get the r squared value. So if you remember from last week, the correlation coefficient had to be a number between -1 and +1. What happens when you square any number inside that range? It must come out to be a number between 0 and 1, the r squared value. Okay? All good so far? That's a tricky part of the semester, I think, is understanding this idea of variation in terms of, the equation of the line. How much variation is explained by this, how much variation is explained by that. It's not necessarily an intuitive kind of thing to wrap your head around. But it is very similar to analysis of variance. So understanding that topic may help you also understand this one. So now we know what we're doing. Let's actually plug in the numbers and get it for the metacarpus and the stature example. We've got our residual sums of squares. We've got our squared deviations. You plug it all in and you get an r squared value of 0.733. Okay? So we reckon that that line for that particular set of data explains about 73% of the variation in stature. Okay, because there's other things that affect your stature, right? And again, it's not really the length of your metacarpus that is having a cause and effect relationship on your height. They are related because they should be proportional to your overall skeleton based on your genetics, your environment, your nutrition. There's a bunch of factors going in there, but how much of it can we account for just by considering proportionality of your skeleton, right? That's 73%, it turns out. The correlation coefficient that we had last week for this data was 0.856. So let's put it to the test. If I square that number, 0.856, where are we? 0.856 squared comes out to be 0.733, rounded to 3 decimal places. So there you go. We've worked it out 2 different ways. One using the correlation coefficient and squaring it, and one using the residual sums of squares. You get the same value as you should. Okay? So the correlation coefficient just tells you how strong the linear relationship is. But you can talk about a correlation coefficient without ever talking about the equation of the line of best fit. Okay? R squared is really referring to the line that best fits the data. Correlation just says, yes, there's a linear correlation, but it doesn't say anything about the line itself. It just says they are related. But then, obviously, again, those numbers are related to each other. Are we happy with that? Okay, so it might be... Yeah, so that's probably a good spot to take a break, because that's a pretty heavy going part of the lecture. So it's about 5 to 10 now, so if you want to leave and come back, aim to be back about 10, and we'll keep going. Okay. All right. So that's the R squared, coefficient of determination. We'll do another hypothesis test on the slope. This time, though, instead of testing for whether or not it's equal to or different from 0, we'll test whether it's different from some specific value other than 0. And we're going to look at another set of data, and this data we've actually used in the practicals before. It's the citrus data. And inside that data, there were 2 columns that corresponded to measurements of total acidity for the samples that these labs were given. And the total acidity was measured by titration or with some kind of handheld meter. And we've got 2 quantitative variables there, measurements of acidity, total acidity. However they measure it, I don't know, it doesn't matter, but they are quantitative variables. If those 2 measurements for the particular samples, I forget what it was either batches of oranges or like orange juice or something, doesn't matter. Whatever it was that they were measuring, if they were measuring the same thing, those 2 methods of measuring acidity, if they're doing the same job, they should be getting the same results. In which case, the scatter plot should have a line of best fit that has a slope of 1. Okay? They're measuring the same thing. This one should get this value, this one should get this value. There should be a 1-to-1 relationship. They should have a slope of 1. So we could test that. We could say, okay, given the sample data that we've got, do we have evidence that one of them is measuring things significantly differently than the other? So this is the idea. We've got a scatter plot. In that plot, we've drawn 2 lines. The blue line would be the line that we expect to see. That's the line y equals x. That's the line that has a slope equal to 1. Okay, that's what I'm expecting to see if these 2 things are actually measuring acidity the same. What I actually got from the sample data was the red line of best fit. Okay? So again, you would not expect, even if they are measuring the same thing on average, you don't necessarily expect to get bang on a line with a slope equal to 1. There's going to be some variation around there anytime you take a sample. So we ask the question, is the red line a fluke? Could this have happened by chance, or is there actually something significant going on? Is one of these measuring things significantly differently than the other? And the simple way to ask and answer that question is to ask, is the slope of the line different from 1? Okay, the red line, is it significantly different from what we expect to see if they're measuring the same thing? Okay, so we've got TA by titration along the horizontal axis and TA by some other electronic or handheld meter, I'm not sure, I can't remember what it was, doesn't matter, along the y-axis. Are these 2 methods of measuring total acidity the same? So the hypothesis test is now not for a null hypothesis of the slope being equal to 0, but equal to a specific value. Okay, and nothing else changes. This is the same test statistic we had before, but before B0 was 0, so it didn't appear there. Okay, so it's still the same test statistic, still a t-distribution with n minus 2 degrees of freedom. Nothing has changed. So that's the test we want to do. We're going to assume that maybe titration is the gold standard. That's the best method of measuring acidity. So really what we're doing is we're comparing this guy, the meter, to the titration and saying, is it doing as good a job? Is it getting the same results? We're going to assume this one's okay. This one's fine. It's doing what it should. This is well known to work. Is the meter getting the same stuff? Or do we have evidence to suggest that it's measuring it differently? Okay. So we simply want to say, is the slope equal to 1? For the regression line, they haven't gone through the whole song and dance. They've just given us the numbers, again, which is typical of maybe an exam question or what you'll do in the pracs. You'll get the numbers from Archimedes. You're not going to have to calculate huge sums of squares. They tell us the intercept is about 0.367 and the slope is about 0.7. So the slope is not 1, okay? But is it a big difference from 1? That's where we need to say, how big is that difference? How far away is our sample estimate, 0.706, from what we expected to get in terms of multiples of the standard error? And they've given us the standard error. They've obviously, again, you would be given that by Archimedes. And tells us that the test statistic comes out to be about negative 3.2. So again, looks like a big difference, right? 3 standard deviations below where we expected to be. If the slope were 1, the p-value is therefore going to be very small. Comes out to be, really, it's the same p-value we had before, to within some rounding, 0.0032. Very small, obviously a significant result. So we've got evidence to suggest that that meter is not measuring acidity in the way it's supposed to. It's not doing a good job. Okay, titration, we're assuming that does a good job. When we got the line of best fit for the scatter plot of titration versus the meter, they're both measuring the same sample. They should be getting the same result. Turns out they're not getting the same result. There is a significant difference there. The p-value is less than 5%, it's less than 1%. Therefore, we say we've got evidence to suggest that the slope is different from 1. Okay. Some software, R Commander won't do this from memory. But just as an FYI, in case you see it when you go out into the real world and dealing with other statistics packages aside from R Commander, some software will quote the F statistic for that rather than the T statistic. But the F statistic is just the square of the T statistic. The p-value will be identical. That's because you can work out all this discussion that we've had about sums of squares and everything is really an analysis of variance discussion. We didn't phrase it that way, but you may have suspected that to be the case when we talked about residual sums of squares and the squared deviations of the x's and the y's and from the line. It was really the same kind of conversation we had when we did analysis of variance. So it's no surprise that you can get an F statistic as well. But we're not going to worry about that. The relationship between simple linear regression and analysis of variance, we're not going to worry about that. Really, it's easier to talk about it in terms of the way we've discussed it rather than analysis of variance, as long as you understand what you're doing is the end game, right? In terms of analysis of variance or simple linear regression, the way we've described it, as long as you understand what's happening, that's fine. The basic ideas are there. Quantitative versus quantitative, linear relationship, correlation, coefficient of determination, all that kind of stuff. If you have an intuitive sense of what's going on, you'll be fine. So any questions about that? Calculate the test statistic based on the difference from what we expected in terms of multiples of the standard error. So that's sort of the first big chunk out of the way. The next chunk is going back to what I said at the start of the lecture, testing the assumptions that we make when we do simple linear regression. So the first two, we don't need to test them. The first one, we kind of have to, we would test that by doing a scatter plot. Is there a real linear relationship between the two things? Look at the scatter plot. Does it look linear? That's basically the best we can do. We can't do more than what we've been given in terms of our sample data. So you'd make a scatter plot, see if it looks linear. The second thing, the observations should be independent when you do simple linear regression. That goes to experimental design. Did you make sure that there was nothing influencing one observation compared to the next when you took all those values? It's really 3 and 4 that require some knowledge of statistics to tackle. Can we check whether the variation around the line is normally distributed and whether they have equal variance along the whole way? Okay, so to check these assumptions, we're going to talk about the residuals again. So we can't check the normality of the response variables using a normal probability plot in this case directly. That's what we've done in the past. Remember that the normal probability plot I showed you for the computer skills test, right? Very simple. You've got the computer skills test score across all campuses, make a normal probability plot, there you go. You can see if it's normally distributed or not. You can't do that for the residuals. If I want to check, where's my plot? Down here. I want to check these two things. Based on my sample data, use a darker one, I want to say, does it seem like these guys are densely packed closer to the line and more spread out further away from the line? For every single x value along the entire thing, and are they all having the same variance? So I should get, if I try and draw a little density curve, look at it sideways, they should be normally distributed around the line. All of the values, they should peak around the line. Most of my values should be there, and they should peak in a way that is normally distributed. Okay, so that's the way you try and think of it. Turn your head on its side, look at the picture. Each response variable for any particular value of x should have that distribution. They should all be normally distributed. That's the first thing we want to check. However, we can't check that because all those normal distributions all have a different mean. This one here this normal distribution, as a mean, it's centered on about 167, maybe. This one here is centered on about 170 or 171. This one here, centered on about 175 or 174, right? They all have a different mean. So that's the first problem. I can't just put all of the residuals into one big set of numbers and get a normal probability plot, because they're not all coming from the same distribution. Okay, so they all have a different mean. So instead of doing that, instead of putting the response variables in, I do put the residuals in. I say the residuals are the difference between what I observed and what I expected, and they should all have a mean of 0, okay? Because most of them should be very close to the line. They should not be very far away. They should have an average of 0. So that's the first thing I'll do. Instead of talking about the response variables themselves, the y values, I talk about the residuals. How far is it from the center? That. All of those numbers, all of those values should have a mean of 0. So that solves our first problem. Our second problem is that they don't all have the same variance. They should in the population. In the entire population of everything, every single response variable, no matter where we are along the scatter plot, they should all have the same spread. I go from one point to the other, the points should be spread around here, the same as they are around here, the same as they are around here. The number for the variation should be the same. We don't have that from our sample data. We've only got so many points per variable, right? This one here is my only way I can estimate the variance of the response variable around that point. I've got one number. The squared deviation, the squared residual, is the variance for that particular point. Obviously, that number is not the same as this number, is it? So I need to estimate the variance for all of the numbers at every single point, and the way I do that is the S value, which was the average of the residual sums of squares. I'll just put RSS. Okay, that's our best estimate for the variance. We take all of those residuals, square them, divide by the number of things minus 2, the number of degrees of freedom, and we say that's our best estimate. That number, whatever S is, should represent the spread of all the values around the line. It should be the same number at every point, S, 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 S. That's how we estimate it. Okay, so that's the idea. And it's getting a bit complicated now. The ideas are getting more sophisticated. So we're going to look at the residuals. They should all have the same mean. We want to say, are they normally distributed? And is their variance the same? So we have to take something called a studentized residual, because the variances are not the same, as we said. Each point, each response variable that we had in that scatter plot, the variance around the line was different for each one. It was the squared deviation, the squared residual. They're all different. So we're going to take something called a studentized residual. The name sounds weird. It's related to the student's t-distribution. The reason, I don't know if you remember, when we first talked about the t-distribution, we came across the name was the student's t-distribution. The only reason it's called that is because the guy who discovered it, William Gosse, I can't remember, he worked for the Guinness factory in Ireland. They were sus on employees publishing scientific papers in case they gave away any of their secret Guinness brewing secrets. So he published it under a pseudonym of student, so no one knew where he worked and wouldn't try and look into his paper to figure out what they were doing at the Guinness factory. He was quality testing, basically. Wanted to test if the Guinness was coming out to scratch. But he had very small sample sizes, right? So his problem was, how can I get valid statistics when I have a small sample size? That's where the t-distribution came from, right? Came from Guinness. So be thankful for that. So it was just called student because he used the pseudonym student. It's called a studentized residual because it's the same thing. It's going to use a t-distribution. We've got a small sample size to try and estimate that variance around the line. So each squared residual, they're not all going to be the same. We have to scale them by an estimate of the variance. That's the rough idea. So we take each of those numbers, each of those squared residuals. Let me clean this up a bit. Each of those squared residuals, they're obviously not equal, but they're my best estimate at each point for the variation around the line at that point. I take those numbers and then divide them by my estimate of the total variance, that one there. That's not the true mathematical way they do it. That's the rough idea, okay? We're not going to worry about the maths. It's way too complicated, but that's the idea. So now that we've done all that, we're looking at the residuals, and then we studentize them, we scale them by a certain amount. We've gotten all that annoying stuff out of the way. Now we can use a normal probability plot. We use a normal probability plot on all of those residual values once we have scaled them by an appropriate amount. And now the normal probability plot just works the same way as any other normal probability plot. We have points outside of the confidence envelope, so it's not normally distributed. Simple as that. Happy with that? You'll notice that the quantiles along the horizontal axis now are from a t-distribution, not from a normal distribution. That's the only difference to the normal probability plots you've done before. But it's the same idea. This one here is residuals against fitted values. So fitted values, they like to keep it annoying and use a different name every time. Fitted values is your predicted value, your y hat from your linear model. Along the horizontal axis, they're the values predicted by the linear model. Along the vertical axis, we have the residuals. So this is really, I mean, I feel like this is overkill to have a plot like this. If you were to look at the titration plot, where is it? This is all it's doing. We say, what are all my fitted values for every point there? There's one. Sorry, all the actual observed values or fitted values from the line at each point. Oops, OneNote's having a heart attack again. From each point, what was the corresponding y value predicted by the line, etc., etc. And then we compare that to the residual. Here's a residual in red, here's a residual in red, here's a residual in red. What were all the corresponding values for those residuals predicted by the line? And you plot them one against another in their own scatter plot. So all you're doing is checking for whether or not they're the same, right? As I said before, do all the points sort of lie in a corridor? Two parallel lines. If I were to draw them either side of the line, I've got a certain plus or minus around the line. Is everything inside of that range? That's how we check for constant variance. So the first one checks for whether or not they're normally distributed. The second one checks for whether or not the variance is the same. And you can see it does look like the variance is pretty much the same the whole way along, except for a couple of outliers there that seem to be throwing everything off. Okay. Any questions? Here's a counterexample. Here's a residuals versus fitted plot where the variance is not constant. You can see very close down at the low end of the line, the points in the scatter plot are very close to the line. The residuals are very small, very close to zero. But as you start to increase, you get a fanning kind of thing happening. The variance is obviously dependent along the line. Okay, it's changing, it's increasing as we increase in the fitted values. So that is a case where you should not use simple linear regression. The assumption is not being met that the variance is the same. So those are the two assumptions we've checked. Normality, studentized residuals, constant variance, residuals versus fitted. Here's one where it doesn't satisfy the fourth assumption that we had in that slide, that the variation is the same. You should therefore not use simple linear regression. And we'll talk in the coming weeks about what you can do instead. Okay, we'll change that data to make it look linear. We'll screw around with it a bit so that we can deal with it later on. The last thing I'll say, we're going to cover this in the practicals, but I wanted to mention a couple of things about this output now, just to reinforce the discussion we had about the test statistic for the slope, for instance. So you can see a whole bunch of stuff. There's a lot of stuff going on. It's hard to break it all down. We'll break it down a bit more in the pracs. But for now, I just wanted to do a simple calculation for a test statistic because this is the kind of thing you may be asked to do in a quiz or in an exam. Here's the output. They might block some things out. So maybe they block out this guy here and ask you to work out the test statistic. So I'll break it down for you. This is the output you get from simple linear regression. One row in this table corresponds to the y-intercepts. So the a hat value. A hat was our best estimate for the y-intercept. And it gives you a bunch of values corresponding to that number. The first one is the number itself, 0.367. That is our estimate of A hat. So in the equation of the line, Y hat equals A hat, 0.367. Okay? Y equals A hat plus B hat times X. So we've got our A hat. We've got our estimate for the intercept. What's our estimate for the slope? Unfortunately, they don't label the slope as clearly as they do the intercept. They will give it the name of whichever variable is the predictor or explanatory variable, the x-axis variable. For this particular Archimedes output, this is from the total acidity measurements. So the x-axis, if you remember, was total acidity measured by titration. So they give the slope the name of the x-axis variable. Why? Because Archimedes is capable of doing capable of doing linear regression that's not simple. As I said before, you can have a linear regression where you have some slope estimate for one variable plus another for another variable. You can have more than one variable, okay? So Archimedes will break it down for you like that. It will name each one of those values, the slope here, the slope here, the slope here, for each corresponding variable. So it just gives it that name. In simple linear regression, it just seems confusing because we only have one variable. So it's like, why didn't you just call it the slope for me? That's why. Because you may have more than one variable, and it will therefore name each of them according to its corresponding explanatory name, explanatory variable name. So anyway, that's B hat. And it's telling us that the estimate for B hat is 0.70563. So there you go. That's one common thing you may be asked to do in an exam, is write down the equation of the line given the output. So you read off those two numbers and don't swap them around. Be very careful. First one's your intercept, second one is your slope. So that slope one should be the number that sits in front of x, okay? The slope is always the number that sits in front of x. So you've got 0.36 plus 0.7 times x. Happy with that? So those are the two numbers there. We've broken them down. They're the estimates for each one of those values. The next value is the standard error. So this is telling you what was the spread of all sample statistics, all sample estimates that you could get for the intercept and the slope. That's what you need to calculate the test statistic. And that's what I want to do now. I just want to calculate the test statistic for the slope, for instance. So Archimedes by default, when it calculates these test statistics, its null hypothesis is that the statistic is equal to 0, and the alternative is that it is different from 0. That's what it always does by default. If you want to do a different number other than 0, you have to do it yourself. In which case, you would also need to work out the p-value yourself. So the test statistic and p-value it gives you are for it being equal to or different than 0. So let's say I want to work out what is the test statistic for my slope. My slope being different from 0. And this is why I thought I would mention it. Does anyone remember, off the top of their head, what's the formula for the test statistic in general? What do you plug in? This is the part where you actually start to learn, is when you try and apply it yourself. You need to sit down without anyone there to help you and be like, what do I do? What do you do? What's the test statistic for testing whether or not the slope is different from 0? How do you calculate it? Always go back and think, what are you doing? I'm saying, how far is my test statistic, how far is my sample statistic from what I expected? I expect 0. How far away is this from 0 in terms of multiples of what? What's the name of it? You don't need to tell me the formula, just what's the name of? Standard error, exactly, standard error. Okay? So now I've got everything I need from Archimedes to work out that test statistic. It tells me the estimate was 0.70563. 0.70563 minus 0, obviously, just leaves it as that. And it tells me the standard error is 0.09188. Okay? If I plug that into my calculator now, oh, there it is, 0.7 70563 divided by 0.09188. I get a test statistic of 7.68 to 2 decimal places. So let me uncover it now and check, did I get the right answer? Yes, I did, 7.68. That's what our commander told me it was. Okay. So that's the idea. You may come across the situation in the final exam, just like we said with analysis of variance tables. They block 1 or 2 numbers out. You have to work out the rest yourself. And you've seen that as well in like the computer skills test and the quizzes. So you just need to know what each one of them is. So there's your standard error. There's the corresponding test statistic. So for the intercept and the slope, it always does it by default different from 0. And your p-value is therefore for it being different from 0. If you want to test is it different from 1, you need to calculate the test statistic as being b hat minus 1. Okay? And then plug it into your calculator. And then you would need to calculate the p-value yourself, because this one here is specifically only for being different from 0. Okay? The last thing I'll mention is that we get the r-squared values down here. You actually get 2 of them. They're very close to each other, but you'll only want to pick one of them, and we'll talk more about that in the pracs once we get to it. And you see there as well, there's the F statistic, 58.98. That, if you check it, should be the square of 7.68. 7.68 squared, yeah, 58.98, okay? The F statistic is always the square of the T statistic if you're talking about 2 independent samples, which is what we have in a scatter plot, 2 quantitative values, well, they're not independent in this case, but you can still calculate the test statistic. All right, so we'll talk about that more in depth in the pracs. Any questions? Yeah.
Can you draw the graph for the hypothesis test?
Yeah, you mean like the T distribution thing? Yeah. So here's your T distribution. How many degrees of freedom does it have? I don't remember off the top of my head for this particular data. It probably should tell me in the R-Commander output. There you go, 30 degrees of freedom. 30 degrees of freedom. So it's a T distribution with 30 degrees of freedom. Degrees of freedom. All T distribution and normal distributions are centered on 0. And we say, how far away is our sample statistic, which was 0.7 something, so it's above it. What was the difference between that, 0.75, whatever it was, minus 0, in terms of multiples of the standard error? Okay, so the variance, the measure of the standard deviation of this thing is the standard error, and they told us that that was about 0.09 or something like that. Okay, so that's all it is. It tells you how far away is your sample stat from where you expect it to be. I expected 0 if the null hypothesis were true. And we say, okay, well, that's how far away we are. Does that seem likely to have happened by chance? Okay, I can take sample data from measurements of acidity and say, here's my numbers. It appears as though there's a difference between these 2 measurements, one from the meter and one from the titration. Is it a statistically significant difference, though? Okay, like with when I did analysis of variance for the computer skills test for the campuses. Yeah, Hawkesbury was at the bottom, Campbelltown was at the top. Is that significant, though? Does that mean the Campbelltown students are better? Or could it just have happened by chance? Turns out it could have happened by chance. Same thing going on here. This one was very unlikely to have happened by chance. The chance of it happening was incredibly small. 1.44 times 10 to the minus 8. That's incredibly small. 0.1234567 Okay, very small p-value. Very unlikely to have gotten a slope that different from 0 if the null hypothesis were actually true, if there was no relationship between those 2 variables. Yeah. Does that make sense? Yep. Any other questions? Okay, thanks guys. Thanks for your attention. I'll see you later this afternoon.